I'll go ahead and just do a quick intro, and then I'll let Ethan intro himself, Ethan B. But hello, my name is Ethan Tabler. I'm the project's exec. So typically, I or one of my committee members will be running these workshops, but we do have a special guest today, Ethan Balcik. I'll let him introduce himself, and we'll go from there. Take it away.
Awesome. How's it going, you guys? So my name is Ethan Balcik. I'm the field ops exec for Penn State IEEE. And over the winter break, I did this little project. I made a graphics engine. And we'll talk a little bit more about that later on. We'll do some interactive work with it. But this presentation is going to delve into some of the math, some of the history, and then some of the actual implementation of computer graphics, particularly 3D computer graphics. So that about covers it for me. Ethan, if you have anything else, you can feel free to add it on, or I can just go ahead and start.
Good to go. Take it away.
Cool. All right. So I'm going to start off with this video. Ethan Tabler suggested that I show this video. So let's just take a look at some of these cool pictures. There's a rock. There's a pretty cool landscape. It all looks pretty cool. So would it surprise any of you to know that this is all rendered using software? So none of this is real. None of this is filmed by a camera. This is all software rendering. So that's what we're looking at here. We're looking at the product of basically what we're going to look into today. We're going to look into what makes this happen. Not necessarily at this level of expertise, but we're going to analyze some of the theory and some of the concepts that allow this all to happen, that allow humans to make these really cool pictures that don't actually exist. So that's what we're going to look at. And the first step in doing so is we will look at, well, all right, here's the title slide. We're going to, like I said, we're going to go over 3D graphics. And by the way, if you didn't know, this is the Utah teapot, which we'll talk about later. So the first step in talking about 3D graphics is going over the math and the history of 3D graphics. So what I want to start off with is just a question for each of you. If anybody wants to answer it, feel free to unmute or add it into the chat. So my question is, when do you think that computer graphics was first implemented? Oh, and also Ethan T, by the way, I can't seem to pull up the chat as well. So
Okay,
you may need to,
I'll let you know what people
yeah,
say.
you may need to read off some chat, chat messages if there are any. But the question is, when do you think graphics was first implemented? Computer graphics. And if we have any answers, let me know. If not, I can just move on.
Maria is saying the 70s. Avery says specifically 1984. And Elijah is saying the 50s.
The 50. Okay. So yeah, Elijah is definitely the closest, but it may surprise you. Well, and I'm going to sort of precede this statement with just a note that there is a lot of gray area here, because technically it's not computer graphics because there's no computer backing it, but technically research into the concepts behind computer graphics took place or started taking place around the 1930s is when it's generally recognized to have started. And it's there are two mathematicians whose name escapes me at the moment, who were working on these luminosity images, I think it was called. Ethan and I were looking at this before the workshop, but basically they were just doing research into accurate lighting models, and that's generally recognized to be the first research into computer graphics and like modern computer graphic concepts. There are obviously concepts that long precede that are very relevant, like linear algebra and like the development of, for example, quaternions, which we don't go into here, and I don't even plan on discussing that, and unless anybody's particularly interested in that. But if anybody is interested in that, feel free to bring it up, and I'll sort of go into that at the end of um, the presentation. But all of that stuff happened in sort of the 1800s. This is sort of like the first modern work in graphics. So other than that, does anything here particularly interest anybody here? Does anything like pop out as particularly interesting on this slide? Because I certainly have a favorite member of this slide, which is the Utah teapot, which obviously you guys saw on the first slide. Yeah, yeah, go with your favorite. So yeah, no, I love the Utah teapot. It's really cool. Um, it was, as you can see there, it was made by Martin Newell. It's basically the first or one of the first examples of a mesh, which we will talk about, but it's just a bunch of geometric primitives that make up this 3D object. So it's like a tessellated 3D object. Um, and like you saw here, if we go back, he used squares. What we'll be using today are triangles. Okay, and so that's sort of the first half of the history behind computer graphics, and now the latter half of the history of computer graphics is basically just the story of computer abstraction. As you can see, I added some points there about so Jim Clark's geometry engine, which later became Silicon Graphics, which later became OpenGL, which is what we're using. And then obviously the biggest point on here I would say is just the Jim Clark for Kimberly Clark. Is that this? Are you asking if that's the same person?
I think it might be.
Really?
I'm joking.
I mean, that would be interesting if some dude left behind his career in graphics.
He would have been like 5 when he did this. So super interesting.
Yeah. Anyways, yeah. So there's that point, but probably the most significant point here on this slide is just the development of the GPU in the 1990s. And that has since, I mean, it's literally just a piece of hardware that's optimized for graphics, just because we're so visually dependent on being like, we're so dependent on the ability to see things going on the screen and to understand like system statuses and everything. So that the reason that the GPU is so huge is not just because of 3D graphics, but also just because humans are visual creatures, and so they like to see things. So the GPU is huge, and it definitely has since become like the main player in computer graphics, as, alongside abstraction as well. So that about cuts it for the history of computer graphics. And so here what we're looking at is a very brief overview of some of the math behind computer graphics. And I'm not going to go into too much rigorous detail on this, but I am going to just give some helpful, like, qualitative descriptions about each of these things, just so that you'll know sort of what you're looking at when we do go into the graphics engine later on. So we have a couple of things here. We have vectors, matrices, scaling, vector addition, matrix vector multiplication, matrix multiplication, and then cross product. And all of these things are going to be important, like I said, when we look into the actual code. So a vector, you can just think of it as, you can think of it as a number of things, but you can think of it as either a point in space, maybe an arrow pointing to a point in space. You can see there's actually a little graphic sort of detailing this here. Or you can just think of it as like a list of numbers, and it can be whatever length you'd like. Same thing with a matrix, except a matrix is a table. So it's a table of, m by n numbers. We'll pretty strictly be dealing with matrices that are like 3 by 3 or 4 by 4. So that they have m equals n basically in terms of their dimensions. But the way that you can think about a matrix conceptually is that it's just a transformation of space. So it changes the shape of space in a certain way, and you can design them in certain ways to do things that are favorable that you want to happen, which we'll look into a particular instance of that on the next slide. Scaling is basically when you take a vector, so like a list of numbers, and you think of it as multiplying in a constant. Like if you want to multiply a vector by 2, think of it as in terms of like you have the number 2 multiply how that works. And it's sort of the same story with vector addition as well. Matrix vector multiplication is a little bit, all right, and we're back. So let me just quickly get things configured here so I can have the chat up and everything. Okay, so vector addition is where we left off, right? I'll just
That was the
start
last thing that I could understand coherently.
Okay. Yeah, so vector addition. If you have two vectors, I mean, we'll only be dealing with vectors of the same length. So I haven't really thought of it as like differently sized vectors, but I don't even know if that's possible. But for the time being, it's just if you have two vectors, it's just adding each component to one another. And as you can see there, it's basically the exact same way that I said it there on the slide. It's adding each coordinate of each vector to one another. And matrix vector multiplication, though, that is a little bit more confusing just because it's order matters in this case. So it's not the same as saying vector matrix multiplication. And doing that as opposed to matrix vector multiplication will provide different results. You don't really have to know very much about the math, like the specific like algorithmic math behind it, but you just need to understand that the conceptual meaning of matrix vector multiplication is that you're applying some transformation that is sort of defined by a matrix to a vector, and so that it then changes the position or the direction of that vector in space in a way. And so then matrix multiplication, which is like if you imagine multiplying multiple matrices by one another, effectively, and again, it's also order matters in this case, so it's equally confusing, but conceptually speaking, it's basically you just combine a bunch of transformations into one, and it's really useful when you're programming because if you have a bunch of different matrices that you want to apply to a bunch of vectors, you could just throw them all into one matrix and then apply just one matrix to that vector. And then the cross product, that's the right-hand rule. Basically, if you pass in two vectors, you get back a vector that is perpendicular to both of them. And you can see this illustrated here in this graphic. The one extra bit of information that I leave out when I say that is that it's also scaled by the angle between the two vectors, or by, I believe, well, it doesn't really matter, but basically all you need to know is that when it's a 90-degree angle, it's the vector that you get back is the same length as the two that you input. And so what you're looking at here is we have two different diagrams that at different, kind of looking from different perspectives of what it looks like to render a 3D scene onto your 2D screen. So, so as you can see here in the left one, you have that little viewer there on the very bottom, and you can see that the viewer is a certain distance from the screen. And then you can see this little line here, which I'll hover over with my mouse. This line here represents the screen. And then what this is saying is this is basically if we didn't have a field of view, so like an angle going from that point where the viewer is to the screen and then into this space, this is really what would get rendered. And this is where you can sort of start to visualize why where things get a little bit complicated, because if you have an item here between these dotted lines, if you're assuming that's your space, it takes up the same amount of the screen as it would here as it does here. Whereas if we add this this angle here, an object that's way in the distance looks a little bit smaller, just like it does in real life. When you see something really far away, it kind of disappears into the distance and gets smaller. And so that's sort of the idea of adding this field of view, is it sort of applies that property. And we'll see exactly how in the next slide, but now this here is just a different way of looking at it. So it's taking this sort of like top-down view of the this two-dimensional view of seeing sort of what this conceptual space looks like, and then it's taking that into more of a three-dimensional representation of like, here's your window, and then here's your render distance, like your render distance kind of like in Minecraft, and this is the space that you're rendering onto this screen. And so I'm just going to stop there and see if anybody has any questions before we move on. Are we feeling good with this?
Yeah, if you have questions and you don't feel comfortable unmuting or speaking out, you can always type your questions into the chat. We do have a few projects committee members that are pretty well versed in this stuff, and they can answer your questions either pretty quickly in there. Maria says no questions, but yay Minecraft. Or if it's something that is worth bringing up that would probably help other people's understanding, we can also definitely talk about it too. But yeah, if you have questions, don't hesitate to put them in the chat for sure.
Cool. So yeah, no questions, but yay Minecraft. Hell yeah. So so what we're looking at here on this slide is basically just taking a good portion of the concepts that we just talked about and showing immediately how exactly those concepts are applied to render objects, conceptually three-dimensional objects, to the screen. And it's really weird because this matrix that you're looking at is 4x4. And so you can say it's a four-dimensional matrix. But it's weird because when you think about projecting a three-dimensional object to a two-dimensional screen, nowhere in that statement is there a mention of 4 dimensions. And the reason that we use a four-dimensional matrix is just so that we can preserve the z-coordinate, because computers are dumb and they need to store things somewhere, and variables change, and so by extending the matrix to the fourth dimension and adding that extra degree of freedom, we can store the z value even in that transformation, and then have that available for us to use after the item is rendered to the screen, and then it comes time to actually color the object. And so just to give a quick rundown of exactly what each of these do, sort of conceptually, is this element sort of applies the property of being able to zoom in and zoom out as the field of view increases and decreases. And so this is what, if you've ever used a camera, this is what happens when you zoom in on a camera lens, or zoom out, is it just changes the field of view. It changes the angle of that you can see visually. It's the same thing. And again, same thing with element 1, 1 here. It's just the only difference is that this element here just normalizes the x and y coordinates. So the screen conceptually just becomes a 1x1 square after we normalize it. And then these here normalize the z coordinate. And like I said in my spiel in the beginning, It's 4 dimensions so that we can preserve the z coordinate even after it gets transformed. So what this slide is covering is, this is just talking about how exactly this works, not necessarily in code, but in code. I don't know if that's a great way of explaining it, but it just introduces the idea of a camera. We sort of just program a conceptual camera in our code. Yeah, you can think of it as pseudocode, where it's just talking about the idea of introducing a camera. It's a great way of thinking of the viewer, and the camera is sort of positioned in a larger space. So there's a limited like subset of that, like subspace, I guess, of that space that's being actually rendered to the camera. Just like you're in a larger space and you can't see behind you. I can't see what's going on behind me unless I rotate and look at what's going on behind me. And so what these slides are going to go into is just how exactly you rotate and translate a camera. So here, it's showing how we define a camera by a couple of vectors. So we have its position, and its position you can think of as a point in space. Obviously, it's positioned somewhere in space. Then we have the up vector, which is defining what direction is up. And by default, we define this as 1 unit in the y direction, or sorry, yeah, the y direction. And then again, we have the forward vector, which is just denoting exactly which direction the camera is looking at. And so by using these, we can represent any like direction and orientation in 3D space. So, and we did have a long discussion about this when we were preparing the workshop, because we were asking the question, couldn't you just represent a camera just using the position and the forward vector? Why do you need an up vector? Because, you know, if you think about it, the forward vector is directional, and so you can just point it at whatever. And the position, you can just change its coordinates and move it all about in space. But what the up vector does is it dictates your orientation. So if you wanted to look at something upside down, how are you going to do that without an up vector? You have nothing to go like this and rotate rotate around about the z-axis so that you can look at something upside down. So that's what the up vector allows you to do, is it allows you to sort of like rotate your head around about the z-axis in space. And so like it says here, we use trig functions for this. And if any of you have taken Math 140, trig functions are a pretty big deal in that class. And basically the way that you think about trig functions are, they sort of just define different points around a circle given certain inputs. And we'll talk about that a little bit more as we go on. But so let's see here. So what we're looking at here is, okay, so this is camera translation. So basically camera translation is just scaling the camera, or sorry, not scaling, moving, like changing the coordinates so that we can move the camera around in space. And we do so by, if we want to move forward and backward, we just sort of add a certain threshold that we come up with to the forward vector, or sorry, to the position vector. So we scale the forward vector down, and we either add it or subtract it. So we move forward and backward. And then moving left and right, this is where, so I'm actually gonna have to go back to the last slide to talk about rotation. So rotating the camera up and down, like I said, is transforming the up vectors y and z coordinates by using trigonometric functions. So you're sort of using a circle to move your head up and down, conceptually speaking. And rotating the camera left and right then takes the, so it takes the x and z coordinates of the forward vector and it transforms it, but it also needs to transform its y coordinate yeah, by the up vector z coordinate, and that effectively keeps the two vectors perpendicular at all times. And that's the reason I went back to this slide, because when we're talking about translation in space, if we want to move left and right, we have to find a vector that denotes exactly what direction is left and right. And to do so, we keep the vectors perpendicular and just take their cross product. And so then we have a vector that we can scale and use to change the position vector of the camera. So enough with all of the math speak. We're going to talk about some actual graphics concepts. So we're going to talk about some graphics libraries starting now, unless anybody wants me to go back and explain something in greater depth. I don't know if I really explained everything as best as I possibly could. So I would assume that there probably would be some questions on at least some of that. But if not, I can keep going. Just let me know. And I'll give you guys a minute to think here. All right. So in that case, it looks like no questions, so we will keep going. So we're going to talk about, well, here the title of this slide is the Kronos group, who right now is in charge of OpenGL. Originally, it was developed by Silicon Graphics, and like it says in the slide, it's since been managed and expanded by the Kronos group. And it's just a giant library of sub-libraries that allows programmers to use these built-in functions to make programming, like computer graphics programming, way easier. And so you can use OpenGL to build things like CAD software or video games or flight simulators. There are a lot of applications, pretty much anything that relies on there being a virtual 3D space. And right there, what you see is a bunch of other 3D 3D graphics libraries that are owned by the Kronos group or managed by the Kronos group and are used for various purposes. So Vulkan, for example, is one that if any of you play video games, you probably have heard of Vulkan at some point. And here are some other graphics libraries that are pretty famous and have been used for a number of things. For one, a really cool fact is that so Microsoft DirectX is one of Microsoft's past graphics engines, which was sort of used as the basis for the name of the Xbox. So that's why the Xbox has the X in front of it, is because they wanted to show that it uses this innovative Microsoft graphics technology. And then, of course, what we have here is we have the RySpec. So that is Pixar's graphics engine. And it's not necessarily like a real-time graphics engine. It's more so just rendering photorealistic scenes, sort of like we saw in that video in the beginning. And then Renderware, that was used on a lot of different like OG game consoles, sort of like the GameCube, which is still to this day my favorite game console. Maria said gasp. I don't know. Why'd you gasp, Maria?
Oh, learn about DirectX for the first time.
I know, right? Crazy stuff. This is mind-blowing stuff. So yeah, so those are just some examples of different graphics engines that exist and that are used for, or have been used for, different things that were pretty, famous, like pretty well known, like the Xbox and like Pixar movies, for example. And so here is where we'll start to dig into some of the specifics of OpenGL. And as I mentioned, OpenGL, it's just another graphics engine, but it's open source as implied by the name. And so it's pretty well documented and it's easy to use and anybody can use it. And so here are just some terms, basically some terminologies, some objects and data types and whatnot. So a vertex, it's just a 3D vector. We've been talking about vectors. I'm assuming you're all pretty comfortable with the idea. That's all a vertex is. Then you have a vertex array object. And so that's just a bunch of lists, that's just a bunch of vertices in a list. And so what a vertex array object is it exists on your GPU. And it's just a bunch of vertex data. Oh, no, sorry. A vertex array object does not exist on your GPU. It exists in the program, and it's just a list of your vertices. A vertex buffer object is the thing that exists on your GPU. And what these vertices actually are making up is a mesh. And a mesh, as we saw with the Utah teapot earlier, it's just a bunch of these geometric primitives. They could be what are called quads, or they could be triangles, whatever primitive you want to use. It's just a bunch of those that are defined by lists of vertices that make up this 3D object. And then the other thing that's on this list here is double buffering. And so double buffering is a technique where you have basically two frames you can think of, and you sort of alternate between those two frames. And when one frame is being displayed in the window, the other frame is being drawn to. And then all you have to do is just switch and then draw to the other frame, and then switch, draw to the other frame. And that's sort of the idea behind double buffering, which is what we'll be using in the graphics engine that we'll be looking at. Then we have shaders. So shaders are what gives the meshes that we just spoke about. It's what gives them color. And so we'll be looking at a vertex shader and a fragment shader. Well, so actually, yeah, so it does more than just color the vertices. It also positions them. So it does the actual job of projecting those vertices on your GPU and then putting them on the screen, basically. And like I said, we'll be looking at a vertex shader and a fragment shader. Geometry shaders, they're pretty important, and they do all sorts of things like tessellation and so like line drawing, for example, as well, rasterization. But OpenGL actually has a default geometry shader that it uses if you don't feed it one. So we don't really have to worry about that so much. And so this is sort of just the pipeline, or you can think of it as like an assembly line, where the input is a mesh or a bunch of vertices. And these are the different processes that each vertex goes through. And then the output is the object on the screen. So the, yeah, and like I said, vertex processing, projection takes place in the vertex shader. Vertex processing happens with the geometry shader, and then coloring happens in the fragment shader. And it looks like Ethan wanted to add an example here as well.
Yeah, so just kind of bouncing off of what Ethan B is talking about with vertexes, with meshes, with shaders, all of that. In the video that you guys saw at the very beginning of the workshop, what makes that look so realistic is their use of very modern shaders, very modern meshes and stuff. And actually, if you wouldn't mind, I just want to share my screen for just a second to show off some of the shaders that were used. Hold on, I'm going to resize my screen. It might make a little bit of a weird motion. Okay, can you guys see what I'm looking at here? Building the dark future of Cyberpunk 2077. Okay.
Yep.
So this is Quixel. They are a company that does all sorts of mesh manipulation and fabrication, and they take these real life objects. So in that video that you watched, they actually went to Iceland and they took believe it was like 8K pictures of these rocks and just like outcroppings and stuff. And they actually turned them into meshes and integrated lighting shaders and all sorts of things. And these are actually like all free for you to use. But I just wanted to show, like, if we're looking at meshes, so this island here is a great example. This is probably about 400 to 500 different meshes that were made, and they're all just made up of tiny little triangles. So when Ethan B was talking about you can use triangles or you could use quads. So think about it as either triangles or squares, rectangles that make up these shapes. And so they can stitch them all together, and they can use shaders to render the lighting and the colors and stuff, and the textures as well. And you get a scene like this. So when Ethan B is talking about, you know, what this is what a mesh is, think about this giant rock structure. That could just be all one mesh, and is literally just a fabrication of a bunch of triangles that have a texture applied to them. And then you're using the shaders that he mentioned to make them look a certain way with the sun or with the color of the rocks and stuff like that. So just wanted to give an example of what he's talking about so that we have kind of a mental image going on in our brains.
Yeah, and if oh wait, actually let me optimize this. And if anybody can actually make those meshes happen in my engine, bonus points. So anyways, we are going to move on to the actual engine itself. So good segue. And let me get my stuff reorganized here. Just get my chat window up. Okay. And so in order to do so, I just want to give a quick refresher on some object-oriented programming, which is what was used to create the graphics engine that we'll be working with today. And so sort of here's just a list of some concepts that are important, and same thing with the next slide. There's more concepts that are important to understand. And I'll start off with the idea of a class. So a class is something that it's basically just a template for an object. I know that probably doesn't really help, but it's where you define exactly what data is going to be contained and what functions are going to be contained by an object when you actually create it. And then an object you can just think of as an instance of that class. So it's like if you created a class of specifying a dog, you know, you might specify breed, you might specify height, you might specify weight. And then if you also might want to add functions too. So you might add run, bark, wag tail, and what have you. So when you just have the class, like nothing's actually going on. You just kind of have a file that's specifying all of that. But when you actually instantiate the object of that type class, or sorry, of type dog, in using my example, then you have an actual dog that can run, bark, wag tail, and has some height, weight, breed data. So that's sort of the relationship there between class and object. And then basically what we're looking at the bottom of this slide is a number of like types of methods in a class, or types of functions within a class. So for example, we have a constructor. That is a function that you call to actually do the instantiating of that object. And then the destructor, you don't actually have to call it, but at least in C++. And but all it does is it just destroys that object from memory. And then getters and setters are sort of a part of the object-oriented philosophy, where you have this data that's contained in an object that you don't access directly, but you access it by using a function that just returns that point of data. And it just allows sort of an extra layer of encapsulation on that data. And so to expand on the idea of data within a class, we have different types of data that can be stored. So I had mentioned that we'll have data within a class that's it's private. You don't want to access it directly. And so that's the idea of a private variable, but there's also public variables. So there are variables that you can access freely, where you can just, if you have an instance of a class, you can just say, hey, give me this piece of data that you have, and you can just get it. Otherwise, if it's private, you might have to call a function to get it. Or there may not be a function to get it at all. It might just be totally private. And then the third type of variable that, at least that's important for our use, is a static variable. And so what static means, and it's important that you understand exactly what the relationship between class and object is to understand this, but a static variable is, you can think of as contained by the class and not the instances of the object. So it's constant across all instances of the object. So no matter how many dogs you create, maybe you decide to add like a species data point, which is static because they're all dogs. And I mean, that's probably a pretty weak example of why you might use a static variable, but that's really the idea, is that every single instance of that class shares a pointer to the same exact variable or function. And then the third thing that we'll talk about just in this object-oriented discussion is UML. And the reason that we want to talk about this, it's not super important to the actual engine itself, but it is important because it helps us visualize the engine using UML. And it's just a way of visualizing any object-oriented software, where it uses these boxes to represent objects and then arrows to represent relationships between objects. And I guess the use of an acronym to describe it, UML, and literally the term language, makes it seem like it's a programming language. It's not. It's just a standard way of visualizing object-oriented programs. And so here we have sort of my implementation of a UML diagram describing the graphics engine that we'll be working with. And so we have this main file here. It's not really a class, but it's a C++ file. And what it does is it instantiates all of these different objects. So it creates instances of them. So it creates a window, for example. It creates some shaders. It creates a camera. It creates a bunch of vertices, and it also creates some transforms as well that we can apply to the meshes that it creates. So I know that's a lot, but the other aspect to this also is that during our discussion of some OpenGL terminology, we also have this view of the CPU side versus the GPU side, where we can see that certain things are just references from this side of the program to the GPU, like to the vertex buffer object. Like we said, vertex buffer objects are just a bunch of bits, a ton of bits that are stored on the GPU, and you have some reference to it. Sorry about that. You have some reference to it from the CPU side that you can call and send it through the graphics pipeline. And then the same thing with our shaders. Our shader programs also exist on the GPU. And then this GL context is, what a GL context is in OpenGL terminology, is it just allows us to actually access all of this stuff. And so that's in our window, because our window is sort of the controller of the whole thing. And so here is the main loop of the graphics engine. And if you guys did go ahead and download like if you cloned the repository and you have it, and you have Visual Studio, you know, you watched the setup video and everything, You can go ahead and open this up now if you'd like, and sort of follow along as we just look through things, because there will be some interactive exercises that take place. So is there anybody that actually has this open right now? Because if not, I can also open mine as well, and sort of, yeah, Maria said she doesn't. I can always open mine and sort of walk you guys through some of it in real
Yeah.
time.
Would you mind just, you have the code here, but it might also be nice to go ahead and walk through a little bit more. You can also zoom in a little bit more so people can see better.
Yeah. Oh, so Elijah says he has it up.
Oh, nice. Okay.
Cool. So,
I've
all
got
right.
mine.
So, I mean, here's how I'm going to put it is like, would you rather, because there are some slides that I still do want to show, but would you rather I walk through it and you ask some questions, or would you rather me go through these slides and then maybe we could do the interactive stuff next? Or because at this point, it's just kind of however we want to go through it, we can go through it. And you can feel free to unmute if you'd like.
So I see the slides that you have, and actually I forgot that you do have a couple of like little flow charts in there. So maybe it would be best to show kind of the flow of the program, and then we can dive into it like you had suggested.
Okay. Yeah.
But Elijah, any thoughts on that?
I mean, I don't mind. I just whatever works for everybody else.
Okay. Ethan,
Cool.
it's at your discretion.
Sweet. All right. So yeah, so what you're looking at here is the main loop, and this is I mean, if you've ever programmed in the Arduino environment, you'll know that that's sort of what you're programming when you program that loop function. Is this just runs continuously when you execute your program, and so this is what happens. This is just the cycle that it goes through every single time that that like as it's running the program. And so what it does is it clears the screen. So like we said, we're double buffering, and so it clears the screen using a certain color. Like I said in that comment, I chose to use dark blue. Then what we do next is we take, and it's also important to note here, which is why I think it might be valuable to actually like look through it in the environment, is above we have a bunch of stuff that we instantiated. It's just sort of implied that we have everything we need here. But so here what you see is that we're updating our transform because we're applying our transform every pass through the main loop. We also bind the shader program to the shader files. That has since changed. And actually there may be things in this screenshot that aren't in the main loop that you guys see, because they're just things that I realized don't need to really be in there. Like for example, the clear color, when I specify that, it only needs to be set once. And then, but then the GL clear function, that has to be called every loop. So you're clearing the screen once again. And again, it's the same thing with binding the shader program. That only needs to be run once at the beginning of the program. After that, you don't need to run bind again. But you do need to run update. That's a function that, well, these are all functions that I wrote. But update basically sends in our transform and our camera, and then that is used eventually to, it's that data is sent to the GPU side and sent into our shader programs, and it's used to actually draw the vertices that we have on the screen. And then mesh.draw is just what actually calls that. It's what actually executes the shader programs that we have. And then the fragment shader.update function, that just sends in our window coordinates. And the reason that's even in there is because there's that, if you're, I don't know if any of you have run the program, but the triangles have this weird funky color going on, and I use the window dimensions to make that happen, where I basically just added this simple little conditional statement where it was like, color this pixel this color if it shows up at this point on the screen. And it creates a pretty cool effect if you get somewhat close to the triangles that are on screen. And then here, this window.update function, it pulls for input and it actually does the swapping of the buffers when we talked about double buffering. That's the whole point of that function. And then also, last but not least, we have a transform counter, which depending on how good your processor is, you may want to make this smaller if it's very fast, because you might see like really fast rotation going on. Or you might want to make it larger if it's kind of slow, so then it rotates more in the same amount of time. If that makes any sense. Anyways, I'll move on. And so this is what our mesh looks like in the software. It's just a list of vertices. Like it's exactly how I described it before. It's literally an array of vertices. And that's not necessarily how it should be, because typically the way that meshes are utilized in software and shared between graphics engines is they're defined in a standardized type of file that can be read in a standard manner. So when Ethan said that the island thing that was made up of all sorts of different meshes, it was freely available. Well, you download it and you get a file that contains this standardized mesh data, and you have to actually have the capability of reading that in, which is, it's not necessarily that hard to implement it. So when I sort of alluded to, bonus points if somebody can figure out how to read those meshes in, we could hypothetically do that. It's just, I just didn't really feel like implementing it for this, so I was lazy. But this isn't how meshes should be defined. They should be read in from files. Now, our shaders are read in from files, and this is sort of showing part of that process. This is showing all that goes into the vertex shader on the GPU side. So this is on the CPU side, and this is the GPU side, where we have this this shader.update function that we talked about. It gets the camera's view projection, so that's the sort of the projection matrix with some additional stuff, and then the transform. So the matrix from the transform, those are multiplied together. So we just combine those into one matrix. And then we take that and some other data and we just send that over to the GPU, which is here. And so the GPU has that now. And then when we get to our mesh.draw function, that actually tells the GPU, all right, we're drawing some triangles and we're drawing this many vertices. Now go ahead and do that. And so you have this this shader on your GPU that now has all of this information, and it's being told to go through its process of transforming all of these vectors that it's getting. And so that's what it does. And so then here we can see, after that's done, we have the output of the vertex shader, which is just a stream of vertices, of particularly transformed vertices. And then we have here from this shader.update function, which what is it doing here? Okay, so it's sending the screen resolution over to the GPU as well, so we can use that for coloring, which I think that is done pretty typically. That actually wasn't a lazy move on my end, because you typically do use window coordinates to some capacity to color vertices. But anyways, what I'm doing here isn't necessarily how it's always done. Meshes typically have color data inherently, and there is a way to make sure that it's that the GPU understands this, and we could get into that later. But the point is that I'm not using color data that's inherent to the vertices themselves. I'm just kind of deciding to color them a certain color my own way. And so as a result of all of that we just looked through, this is what we get. And as you can see, it's actually doing things that if you do have the program open and you're running it, you can't do yet. So does anybody have this running currently and is not able to translate the camera around or rotate it around? Because I would assume not, unless you guys went above and beyond and actually it tells, okay, yeah, it gives you some output if you click on the window. Yeah, and so that's what we're gonna do now, is we're gonna actually implement this using some of the info that that we went over before. And so I guess here's where it would be mostly important to ask. Actually, I'm just going to go ahead and do it. I'm going to open up my environment here so I can walk through this with you guys. So give me a sec here to just open up Visual Studio and grab the project. Wrong project. All right. And I'll share my screen here. By the way, are you guys getting my, well, actually, let me run it first and make sure. Just let it build real quick here. So are you guys getting this window here? Yes or no? Ugh, it'd be nice if I could open the chat. Okay, yes.
Yeah, so one of the things to notice, you'll see at the top, right next to where it says debug, it'll say debug x86. Make sure it's on x86 and it doesn't accidentally get switched over to x64. It only runs on the x86 instruction set, just the way that it's built. So keep that in mind.
Yeah, and so like Elijah said, actually I might have, okay, yeah. So if you click on the window, it just gives you some output in the command window. But what we want to do is we want to actually be able to rotate and translate the camera. And so, sorry if this is distracting. I'm gonna keep switching back. I can actually move my windows. This is dumb. I'm gonna move the windows themselves from now on. But so, all right. So here's the goal: is first we want to rotate the camera. We want to be able to look around basically. And we have some things that we can work with, which is the mouse's X coordinate, the mouse's Y coordinate, the window aspect ratio, and then the camera up vector, forward vector, and then of course the view projection as well. And so here's where I'm going to ask you guys to come in and, well, I just gave you the answer inadvertently. So here's where I'm going to ask you guys for your thoughts. Does anybody have any idea? I mean, technically, I already gave you the answer for what should go on here, but I don't know. Any thoughts? Throw them out there. I'm just trying to find the function that we need here too. Okay. If there are no thoughts, what I will tell you is that I do have two functions like pre-written that, well, not pre-written, but they're already declared in the camera.cpp file. So open that up too. I should have mentioned that. And they're called update position and update rotation. And I'll share my screen here.
Also, just let me know when you want me to share the other two files that you posted in the drive.
True, yeah. Yeah, if nobody has any particular thoughts as far as like what type of code should go here, what types of operations should go down, then I could just walk through it and then share the files with them so that they can explore. Which I think is what I'll do. So I'll go back into this presentation. Yeah, that Google Drive document, and there will be another one that Ethan just shared, is the rotation function, I believe. And so here's pretty much how it works, and we talked about this before, is to rotate left and right. That's the first step. We have a forward vector, and if you imagine this in like in a 3D space, a Cartesian 3D space with an a y, an x, and a z axis, the forward vector starts at 0, 0, 1 by default. So it's pointing in the z direction, 1 unit in the z direction. And so to look around, all we need to do is just make it point like that, like back and forth, left and right. And so what we do is we use sine and cosine to make this happen. So if you think about it in 2 dimensions as an x and a y axis, sort of traditionally how you would think about sine and cosine. Sine, it returns the vertical coordinate along that circle in the xy plane. And then cosine returns the horizontal coordinate. And so we can sort of take this intuition and map it to the is it the z and x? Yeah, the z and x coordinates of the forward vector. And then basically we can figure out that since by default it's pointing in the forward direction, so it's pointing in the z direction, we would treat the z coordinate, weirdly enough, as the x coordinate on an xy plane, so as the horizontal coordinate, and then the x coordinate as the y coordinate, so the vertical coordinate. And so this way we would know that we'd have to use cosine to get the z coordinate and then sine to get the x coordinate. And so what I did in the update rotation function, if you guys have opened that file already, and you guys can feel free to just copy and paste that into the function, is I sort of restricted it so that you could only look a certain amount left and right. And excuse me as I just navigate over to that document myself, so I can copy and paste it in myself. So yeah, and it's kind of complicated. There's a lot going on there. Also, let me know if there are like formatting issues, because I copied it into a Google Doc, so I don't know if that like screwed with any of the tab, like the spacing, or like how it's sort of organized in the function. But let's just throw all of that into this. Okay, no, it looks good. And so here's the update rotation function, and it's, like I said, very messy. And we've only discussed this part of it. But what about rotating up and down? And in that case, we would do something very similar, where we would sort of imagine the y and z coordinates of the up vector, and we would think about them at like in terms of their default placements, and we know that y is the default direction that the up vector is pointing in. And so then using that, we would say, okay, the y coordinate of the vector, we will use cosine for that. And the z coordinate of the vector, we will use sine for that. And then again, we had this discussion a little bit earlier about the cross product. We want to always make sure that the and it's not also just as a note, it's not just because of the cross product. It's also because OpenGL will go crazy if you don't keep these two vectors perpendicular. But that's what this does here, is it just takes this updated z coordinate here, and it uses that to update the forward vector so that everything works, so that they just stay perpendicular no matter where you're looking in space. And so if you did copy and paste that function in to the code, you'll see that now, which I'm going to run it myself, you can actually look around, and you can look left, you can look right, you can look up and down, and you can really look in any direction, which is pretty cool. But you still can't move around. If you try and use WASD, you can't move in any direction. So that's something that we still have to do, which obviously Ethan already shared that function with you. So maybe you guys have pasted that into the code already, I would assume, but let me go ahead and share the slides explaining that function in a little bit greater depth. So here's the idea, is going into this update position function, we want to be able to use the W, A, S, and D keys to change the position of the camera using the camera's up vector and forward vector, and obviously the view projection. And so again, the way that we would approach this is the position by default is 0, 0, -3. If we wanted to move forward, it's just changing the Z, I believe. So if we want to move forward in the Z direction, then we just change the Z. But it also depends on the direction that we're looking to. So there's that, and you'll see that in the implementation. So it does it uses, oh, I haven't copied it in yet. Let me copy it into my code so I can show you guys in C++. Did I ever even share my screen there? I don't think I shared my screen there. Sorry about
I
that.
can see that.
Yeah, we could see your screen.
Yeah, now I have it shared. Okay.
You mean like before, whenever you were demoing the actual? Like,
yeah.
Yeah, we could see it.
Okay.
Yeah.
Okay. So yeah. So what I was starting to get into there was it just takes the forward vector, which, by the way, as you guys remember, it gets updated when it rotates, so it sort of preserves that rotation, and it just adds all of its coordinates to the position vector. And so this way, no matter which way we are facing, we always move forward relative to ourselves. And so case 0 and 2 are forward and backward. And then case 1 and case 3, well, that is left and right. And you can see with this C product here, that's presumably the cross product of the forward and up vector, which we were so careful to keep perpendicular just so that we can make this happen. And then we get this vector that's perpendicular to both of the forward and up vectors. And then we can, again, apply that to the position vector and update the position of the camera. And also note that this is all multiplied by this threshold here, just to make the animation a little bit cleaner. Because if there was no threshold, we would be, anytime that we would hold down any of the WASD keys, we would move a detectable amount of distance. It would be really choppy, basically, is what I'm trying to say. So like we would be able to tell the fact that we're jumping through space, and it wouldn't look very clean. It wouldn't look like we're moving continuously, basically. And so now I can run this once again. And so now we can see that we have rotation, but we also have movement in 3D space. And there's a weird trippy thing going on there, which we can talk about too if anybody's interested. Ethan Tabler and I had gone over this before and sort of tried to mitigate it a little bit, but there is a reason why that triangle there is sort of overlapping the other triangle in this weird way. It's like this crazy optical illusion. But anyway, to take a step back and appreciate what's going on here, is now we can translate and rotate the camera, which was sort of the goal of that whole exercise. And I wish it could have been a little bit more interactive, but I figured we had already gone through the most of the specifics, so you guys get it. You guys just want to be able to walk around in space and see cool shapes. So, is there any questions in general, having gone through all of that? I know that was a lot. I don't mean to be like overwhelming. And honestly, my train of thought over the course of an hour and a half tends to bounce back and forth. So if there's anything that you felt I didn't explain very well, please let me know so that I can fill you guys in on that maybe in a better way.
It's not really a question, more of just kind of an informative thing. If you guys would like, I can make sure that the presentation for this is shared once we put up the recording for this. And there's also a works cited at the end, which Ethan did a great job at organizing a ton of his sources. And part of this tutorial was actually, or part of this video, this workshop is based on a tutorial that somebody did, what was it, like 3 or 4 years ago or something?
Yeah.
That outlines it pretty well as well.
Yeah, and the guy that he's referring to, it's on YouTube. His name is the Benny Box. If you look him up, I can also send the link to the series itself that I used for this particular engine in the chat. But he goes into some more detail in a number of different series that he's done on 3D graphics programming. And so, for example, I mean, for one, he in one of his series, he is able to actually read in meshes from files, and that was pretty cool. And he also implements a number of techniques that Ethan and I looked into just after I had finished programming all this and putting together the presentation, where like, for example, one is called backface culling. And that is the reason why that weird triangle thing happens, where it seems like the one triangle is overlapping the other, even though it should be behind it. It's because I don't have that implemented. And I also don't have the like the painter's algorithm implemented. And those are both just techniques that use the Z coordinate that we preserved. As you guys remember from that slide about the whole projection matrix thing where we talked about preserving the Z coordinate, we actually use the preserved Z coordinates of those objects in space so that we know the order that we should draw them in. So think about like a Bob Ross show where he's painting, some beautiful landscape. He probably draws the sky first because that's like the furthest thing in the distance, and then he probably draws like the mountains and then like the trees on the mountains, which are a little bit closer in terms of your Z distance from yourself to the tree. So that's the idea behind those algorithms, is it just allows for those objects to be ordered in a certain way so that they're drawn onto the screen correctly and not weirdly like we see in my iteration of a graphics engine.
Cool. Well, does anybody have any questions to follow up what Ethan said? Any questions about how he went about researching for the workshop, how he kind of gathered all of these materials? Is there anything like that? I'm sure you'd be happy to answer. He documented everything very thoroughly. So if there's nothing that you are questioning now, once you go back through the presentation slides, I'm sure there will be certain things that will jump out at you. Maybe that didn't jump out at you tonight, but if you're watching this back or looking at the presentation on Google Drive, there should be a ton of information there as well. Well, if there are no other comments, Ethan B., I will let you close this out.
Sweet. Yeah, so I encourage you guys to just keep playing around with it. I'll also update the GitHub so that it now does account for those two functions that I left out for the sake of education and learning. But no, seriously, there's a lot to digest there, and it legitimately took me like a year to actually understand everything that is going on in that engine. And so like, I know it's a lot. So if you feel confused at all, don't worry about it. If you're interested in graphics, just keep chugging and keep looking at tutorials, and there are tons of resources online and tons of ways that you can get involved in building your own graphics engines and making your own 3D software renderings and whatnot. So I guess in general, that's my advice. And I had a great time putting this together, and I'm glad that you guys popped out. I know that most of the people here were like execs or committee members, but still, it was a ton of fun putting this all together. And the reward is not in the actual presentation itself. The reward is in all the work that went into it. So that's what I'm mostly hype about. So I hope you guys have a great rest of your night with that all being said.